Hey everyone, so here's our next lesson in electrochemistry, and it deals with Gibbs free energy and electroplating. And this is all of electrochemistry. Gibbs free energy is just an extension of galvanic cells, and electroplating is just kind of dimensional analysis, but with electricity instead. So the first thing I'm going to talk about is Gibbs free energy. We'll talk about electroplating later. But what is Gibbs free energy? It's just the measure of potential useful work, okay? It's pretty much just how much work can this galvanic cell do if we have a certain amount of moles of each anode and cathode. And the way that is represented is by delta G, and it is measured in kilojoules per mole. Very similar to our delta H enthalpy, but again, this is just delta G. It is potential useful work. How much work can the cell potentially do? And the main equation we're dealing with today is delta G equals negative NFE. Okay, so what does that negative NFE mean? Well, N just means number of moles of electrons. So if you remember in our last lesson, we'd make the overall reaction for a galvanic cell, and we would have to make the electrons match up. Sometimes we'd have 2 in one and 1 in the other, and we'd have to multiply the other half reaction by 2. Well, that's what N is going to be. It's going to be the amount of electrons we match it to at the end. So if we were matching the electrons to 2, our N would be 2 as well. Okay, and you'll see that in some examples. F is Faraday's constant. Okay, it's just a constant by a scientist who dealt a lot with electricity, and it's 96,485 coulombs per mole of electrons. Okay, and then E naught is just cell potential, and that's what we've been finding in our galvanic cells. Now, in our last lesson, E naught, when it was positive, it was thermodynamically favored or spontaneous. If E naught was negative, or cell potential was negative, it was not thermodynamically favored. It was not spontaneous. We would need a battery. Well, with delta G, if we have a positive G, that means it is not thermodynamically favored. And I'm just going to write thermo, okay? But if it's delta G, it's not thermodynamically favored. It is not spontaneous. But if we have a negative G, it is thermodynamically, and I'll have room to spell this one, dynamically favored, or it is spontaneous. So they're just opposite, right? It's almost the same as delta H. When delta H is negative, it's thermodynamically favored. When delta G is negative, it's thermodynamically favored. When it's positive, it's not spontaneous or not thermodynamically favored. So works the same as H, negative, thermodynamically favored, positive, not. It's the opposite of cell potential, which when cell potential is positive, it is thermodynamically favored. When it is negative, it is not spontaneous or not thermodynamically favored. One more equation that we're going to have to worry about is rat link. And you heard that right, rat link. What is rat link? It's just that delta G equals negative RT ln K. So this is just a really great way to relate Gibbs free energy and equilibrium constant. Okay, that's the main thing we like to do with this. So all you need to know is G is Gibbs free energy, right? We just talked about that. R is another constant, and it is 8.314. All right, so there are two R's now. Remember, there is R from Pivnert, which is 0.08206, and this is R from Ratlink, which is 8.314. Okay, that is on your equation sheet for the AP exam. Just make sure you don't get the R from Pivnert and the R from Ratlink mixed up. T is just temp, or the temperature in Kelvin, and then obviously K is our, since it's uppercase K, it's equilibrium constant. Okay, so we'll be doing that a little bit today as well. We'll be going ahead and we'll be solving delta G, and then we can also go ahead and figure out our equilibrium constant from that as well, or how much of a product we're going to produce. So let's go ahead and let's do an example where we are kind of doing galvanic cells, Gibbs free energy, equilibrium constant all together. All right, everybody, so here's our Gibbs free energy calculation with galvanic cell. So I have a galvanic cell with aluminum and zinc at 298 degrees Kelvin, and where both solutions are at 1 molarity. So that just means in the beaker, those two liquid solutions in there are both at the same concentrations. If they're at different concentrations, that could affect the flow of electrons, and we'll talk about that another time. But what I want you to do from this information is find the half reaction for the anode and the cathode, the overall reaction, the cell potential, the free energy, if it's thermodynamically favored or not, and let's find the equilibrium constant. Okay? So write all of this down, and I'm going to go ahead and erase these so that I have some room to work. So first of all, let's find the half reaction for the anode and the cathode. Well, let's see. We're dealing with aluminum and we're dealing with zinc here. So let's just go ahead and let's write down the standard reduction reactions for both of these. So if I look up aluminum, the standard reduction for it is Al3 plus AQ plus 3 electrons is going to make aluminum solid, and its cell potential is going to be negative 1.66. And then if I look up zincs, it's zinc 2 plus AQ plus, plus 2 electrons, and it's going to make zinc solid, and its reduction potential is negative 0.76. So again, it wanted the half reaction for the anode and the cathode, but these, remember, are both reduced. Well, which one is going to stay reduced? The one that is more positive, right? That is higher. Well, in this case, the one that's going to stay reduced is our zinc, right? Is the more positive number. That aluminum is really negative. It's very not thermodynamically favored. So this one's going to be our reduced one. And then let's go ahead and flip this top one so that we know it's now oxidized. Aluminum solid is going to become Al3 plus aqueous and 3 electrons. And remember, now that we flipped it, it is no longer positive or negative. It is now positive. So now this one is oxidized. Okay. Now let's identify which one's the anode and which one's the cathode, right? Red cat. Reduction happens at the cathode. So this must be my cathode. And ox. At the anode, oxidation occurs. So this must be my anode. So there are my two half reactions. B, it wants the overall reaction, right? So we just combine these guys. But remember, I can't combine them until the electrons are the same, right? We have a 2 and a 3 here. Well, I don't want those to be 2 and 3. I want them to be the same number. Well, to do that, I would have to times my aluminum by 2 and my zinc by 3. So now we're going to have 2Al solid, 2Al3 plus, and 6 electrons. And now we're going to have 3Zn2 plus aqueous plus 6 electrons in now 3 zinc solid. So now my electrons could cancel out, and now my overall reaction is going to be 3 zinc 2 plus aqueous, 2 aluminum solid, and it's going to make 2 aluminum 3 plus aqueous and 3 zinc solid. So there is my overall reaction. Okay, make sure those electrons are the same. Remember, that does not affect our cell potentials at all when we multiply those by 2 and 3. And then it wanted us to find, so this was B, and then for C it wanted us to find cell potential. Well, we just add these guys up, right? 1.66 plus negative 7 or 0.76 will give us a cell potential of 0.9 volts. 0.9 volts. Okay? So now A, B, and C are done. And now remember, in D, it wants us to find the free energy, which is just Gibbs free energy. Okay? So for Gibbs free energy, remember, if we want that, we're going to need negative NFE to find Gibbs free energy. Well, N is the number of moles of electrons that we had from the overall reaction? Well, remember that when we matched them all up, the moles of electrons we had was 6. Okay, it was 2 and 3, but then we had to get them both to 6, so that is what our N is going to be. So it's going to be -6. F is our Faraday's constant, which, if I remember correctly, is 96,485. Let me just make sure I have that right, because I don't have every constant memorized. Yep. And then E is 0.9. So let's multiply all these together and find our Gibbs free energy. So -6 times 0.9 times 96,485. Okay, and this will give us -521,019. But I want you to know that when you solve this, this is going to be in joules. Okay, that's going to be in joules. Well, I don't want joules, right? Remember that delta G is in kilojoules per mole. So let's change this to kilojoules per mole, and that's just moving the decimal over 3 times. So it'll be -521 kilojoules per mole, and that will be D. Okay, thermodynamically favored. It is negative, so yes, it is thermodynamically favored, right? If it's negative, it's favored. If it's positive, it's not favored when it's delta G, right? That makes sense, right? Because when E is positive, it is thermodynamically favored or spontaneous. And so that means that G should be negative, so it should be thermodynamically favored. And then the last one, E, it wants me to find the equilibrium constant, right? For E, well, remember, we got to use delta G equals negative rat link. Okay, negative rat link. So let's go ahead and let's do that. We have to leave delta G in joules. So as our previous one, we want that to stay in joules. So that's going to be -5,000 or 521,019. Okay, it's got to stay in joules. All right. R is 8.314. That is our new constant. Our temperature I gave you for T is 298. And then we got to solve for K. Well, let's just go ahead and let's divide to get ln K by itself. So I'll plug that into my calculator, and you will get 210.3 equals ln K. Well, the inverse of the natural log is e to the, so we'll do e to the 210. And you should get an equilibrium constant of 1.59 times 10 to the 91. Huge, huge. Okay, but we're producing a lot of products here, right? It's a spontaneous reaction. It's thermodynamically favored. It's going to create a lot of products. It's going to want to happen. So you're going to expect a large K or a large equilibrium constant. Okay? So that is an example of combining all those together and getting Gibbs free energy. I'm not going to go too much more into this. You could try this in the practice if you want to. Let's move on to our electroplating problems. So now we are moving on to electroplating problems. Electroplating is just coating a metal in a different type of metal. And the way we do that is that we pretty much run electricity through it in order for those metal atoms to be attracted to the outside of that other metal. And there are some electroplating problems that you will see. The first thing you need to know is amps is current, and it's just coulombs per second, right? Amps is the most dangerous thing in electricity. It is the thing that kills you, not voltage. The amps, you don't want a bunch of coulombs running through you per second. You want a low amperage, but that's a good unit to note. And then Faraday's, you gotta know that it's coulombs over 1 mole of electron. And what we're pretty much doing here is we're just doing dimensional analysis to get from grams of a certain metal to seconds of time it takes to make that amount of metal, okay? And so what we do is we'll convert grams to moles. We'll change moles of the substance to moles of electrons using a mole ratio. We'll convert those moles of electrons to coulombs using Faraday's constant up here and using those units. And then we'll convert those coulombs to seconds using our amps. So let's go ahead and let's dive in and get a couple of these examples done. Alright, so here's our example. How many seconds will it take to electroplate out 5.0 grams of silver from silver nitrate using 20 amps of current? So pretty much what you're doing is that you might put like, I don't know, a crappy metal bracelet into a solution of silver nitrate. If you run current through that metal bracelet, that silver from the silver nitrate will attach to the outside of that bracelet and coat it in a nice layer of silver. It's an easy way to make jewelry look nice. But instead of making it out of pure silver, you just coat the outside with silver. So here we'll have 5 grams of silver, and we're using a 20 amp current, and we want to know how long it's going to take to get 5 grams of silver around a certain piece of metal. So as you could know earlier, is that I got to change grams of whatever I'm dealing with, which in this case is silver. Don't worry, that's silver nitrate. That's just the solution we're working with, but it's just 5 grams of silver. So let's go ahead and let's convert that to moles, as I stated in my first step, right? Moles is our friend. It's always nice just to get everything to moles, because then we can convert it to a lot of things. So 5 divided by the molar mass of silver is 0.06 moles. 0.046 moles, sorry, of silver. And then I believe the next step I had was convert moles of substance to moles of electrons. Well, in order to do that, we're going to need our standard reduction half equation. So what you'll do, again, you'll look at that sheet, and you'll see that silver, for every silver plus ion, if you want to make a solid one, you're going to need 1 electron. So the moles from silver to 1 electron is just 1 to 1. For every 1 silver solid, there is 1 electron. So all we're doing is we're going to do a mole ratio. Again, for every 1 mole of silver solid, there is 1 electron. So we no longer have moles of silver, we have 0.046 moles of electrons. And then I believe in step 3, I said that we got to change this to coulombs using Faraday's constant. So if we look at Faraday's constant, right, it was, I think it was 96,485, and it was coulombs per 1 mole of electrons. And I'm trying to change it to coulombs, right? I want to get it to coulombs. So using these 2 units, would I multiply them together or divide them to get to coulombs? I'd multiply them, right? If I multiply them, moles of electrons cancel out, and I'm just left with coulombs. Okay, so I'll take 0.046 times 96,485, and I will get 4,438 coulombs. Okay, so that's, again, using your units to help you. So grams to moles, moles of substance to moles of electrons to coulombs, and if you remember my last step, I have to use the amperage to go from coulombs to seconds. Well, remember, if I have 20 amps, that's 20 coulombs per second. So how am I going to get from coulombs to seconds using those 2 units? Well, if I divide by 20 coulombs per second, coulombs cancel out, and I'm just left with seconds. So we're going to divide by amps. So we divide by 20, and we realize that it'll take somewhere around 222 seconds. I'm going to have to run that current for 222 seconds in order to electroplate 5 grams of silver. Okay, so what we're doing is we're just using our units to help guide us. You could remember those 4 steps if you want. Grams to moles, moles of substance to moles of electrons, multiply by Faraday's, divide by amp, or you could use your units to help you, okay? Because sometimes we're going to have to go backwards as well. We might have to go from amperage, or how many seconds we run a 20 amp current, to grams of silver. So just be aware of your units and help them guide you. Let's do one more example like this, and then we'll be done for the day. So here I have, you run a 5 amp current for 100 seconds. How much zinc do you produce? So now this is kind of what I was talking about before. This is a situation where now we're not going from grams to seconds, we're going from seconds to grams. So let's go ahead and let's start with what we're given. We're given 100 seconds, right? And now I gotta go from seconds to coulombs if we're working backwards, right? So our fourth to third step, I have to go from seconds to coulombs using amps. Well, remember that amps is coulomb per second. So what do I have to do with these two units just to get coulombs? It looks like I just multiply them, right? If I multiply them, seconds cancel out, and I'm left with coulombs. Specifically, 500 coulombs. So I ran 500 coulombs of current during this whole time, okay? So 500 coulombs, I sent those through, and now remember we got to get to moles of electrons. And by doing that, we use Faraday's constant. Remember, Faraday's constant is 96,485 coulombs for every 1 mole of electrons. Well, 500, 96485 C per 1 moles of electrons. I got to get to moles of electrons. I'm going to divide 500 coulombs by 96,485, right? That way, coulombs cancel out. I'm just left with moles of electrons. So 500 divided by 96,485 will give me 0.0052 moles of electrons. Well, moles of electrons won't help me. I gotta get to moles of what substance I'm dealing with, which is zinc. And if I look back at zinc and look at its reduction potential, it takes 2 electrons to produce 1 zinc solid. So I gotta do a mole ratio here now, where for every 2 moles of electrons, I make 1 zinc solid molecule. So I'm dividing by 2 here. So I divide by 2, 0.0052 divided by 2, and now I have 0.0026 moles of zinc. But again, I don't want moles of zinc. I want grams of zinc. So now I gotta take those moles and multiply it by the molar mass of zinc, which is 65.4. So I multiply it by the molar mass of zinc to get grams of zinc. So this is actually a pretty small amount of zinc. It'll just be about 0.17 grams of zinc is what I produced, okay? So that is our lesson. So now you should be able to deal with Gibbs free energy. Remember that delta G equals negative NFE. You should be able to deal with delta G with terms of equilibrium constant, negative rat link, and now you should be able to handle electroplating problems pretty much using dimensional analysis, using your units to help you get to the right desired product. So that's it. Please try out that practice. Let me know if you have any questions. Have yourselves a great day.